Galileo Galilei famously described the universe as a grand book penned in the language of mathematics. Within this cosmic text, picture a truly exceptional location where nature's forces find a perfect equilibrium. This spot, situated between Earth and our star, is a zone where objects can seemingly hang suspended in space, creating an unseen sanctuary known as Lagrange Point L1, a crucial haven for our most important scientific tools. You can find this distinct area about 1.5 million kilometers from our planet in the direction of the Sun. And it is here that a remarkable physical phenomenon unfolds. The gravitational pull from both Earth and the Sun cancels out in such a way that it establishes an ideal balance. This allows a spacecraft to hold its position with respect to both celestial bodies, much like discovering a calm center in a swirling vortex, a pocket of profound stability within the constant flow of cosmic energies. If you've ever asked yourself how scientists achieve uninterrupted views of cosmic events, the answer resides in these gravitational sanctuaries. By placing telescopes and satellites at the L1 point, they secure an unparalleled advantage: the ability to conduct 24/7 surveillance, completely unimpeded by the shadow of our planet or the blurring effects of its atmosphere. The underlying principles are surprisingly straightforward. Any object placed at L1 orbits the Sun in perfect concert with Earth, effectively holding a constant spot between them in a synchronized celestial ballet. This gravitational balancing act means that a spacecraft needs very little fuel to correct its position, which is an enormous benefit for missions designed to operate for many years. The real-world uses for this specific point in space are vast. For instance, the Solar and Heliospheric Observatory, or SOHO, has spent decades at this unique vantage point, relentlessly studying our star. From this location, it provides scientists with vital information about solar flares and coronal mass ejections, which are events that can disrupt our technology on Earth. Similarly, the Deep Space Climate Observatory, also known as DSCOVR, uses L1 to keep an eye on space weather and analyze our planet's energy budget, acting like a celestial guardian that warns us of approaching dangers from space. However, L1 is only the first of 5 such extraordinary locations in the Earth-Sun system. In each of these zones, a combination of gravity and centrifugal force produces a stable environment for smaller objects, serving as unseen moorings in the immense sea of space. The L2 point is especially compelling. It's situated on the opposite side of Earth from the Sun. Here you will find the James Webb Space Telescope, our premier instrument for observing faraway galaxies and exoplanets. Whereas L1 is perfect for watching the Sun, L2 provides unmatched conditions for peering into deep space, as a telescope there can perpetually face away from our star's glare. It's crucial to realize that spacecraft at these Lagrange points aren't perfectly motionless. To remain in place, they must perform occasional course corrections. The majority trace what are known as halo orbits, distinctive paths that counteract any natural drift and ensure the best possible line of sight to the Sun or Earth, tailored to the specific goals of the mission. The science behind maintaining an object at L1 is a delicate interplay between the gravitational forces and the centrifugal force arising from its orbit. This intricate balance results in a unique area where a vessel can linger using very little energy. For mission planners, this translates into the capacity to design spacecraft that can operate for years, or even decades, without needing constant and expensive adjustments to their trajectory. The strategic value of the L1 point as an early warning system for solar events is immense. A satellite positioned there can spot a solar storm between 15 and 60 minutes before its high-energy particles arrive in our vicinity. While this may not sound like much time, it's enough for space organizations and power grid operators to implement protective protocols, shielding our satellites, astronauts, and critical electronics on the ground from harm. These points were first identified in the 18th century, when French mathematician Joseph-Louis Lagrange theorized their existence. His calculations proved that these gravitational balance zones are a natural feature of any system with two large masses, such as the Earth and Moon, or the Sun and Jupiter. Today, his once theoretical concepts are fundamental to the field of orbital mechanics and the planning of modern space missions. As we look ahead in our exploration of the cosmos, the significance of Lagrange points is set to grow even more. With technological progress and the rise of more ambitious projects, these gravitational safe havens will become indispensable platforms for deploying the sophisticated scientific instruments and advanced telescopes of the future. Now, let's turn our attention to another of our solar system's marvels, the planet Venus, which is full of bewildering contradictions. As our closest planetary neighbor, it displays a truly strange characteristic. A single Venusian day is longer than a full Venusian year. This might sound impossible, but the data confirms this extraordinary reality. To put it in numbers, Venus requires roughly 243 Earth days to spin once on its axis. In contrast, its journey around the Sun, its orbital period, takes only about 225 Earth days. This results in the bizarre circumstance where the planet finishes its annual trip around its star before it has even completed a single rotation. And the oddities don't stop there, because Venus holds another secret. Its rotation is backwards compared to nearly every other planet in our solar system, a behavior known as retrograde rotation. If you were able to stand on its inhospitable surface, you would witness the Sun appearing in the west and disappearing in the east, the exact reverse of our experience here. This inverted spin introduces further complications when determining the actual length of a solar day on the planet. On Venus, the time between one sunrise and the next, known as a solar day, extends for approximately 117 Earth days. This incredibly slow rotation profoundly influences the planet's climate, most notably by nearly eliminating the Coriolis effect, a force that is essential in shaping the weather systems and ocean currents you experience on Earth. This results in extremely sluggish atmospheric circulation near the Venusian surface, which is a stark contrast to the much faster-moving upper layers of its atmosphere, creating a fascinating dynamic. Despite this leisurely spin, the planet's surface is subjected to unimaginable temperatures, exceeding 460 degrees Celsius, making it hotter than even Mercury. The culprit behind this intense heat is a runaway greenhouse effect, which effectively traps solar energy within the planet's dense atmosphere. The combination of prolonged days and a thick, persistent cloud cover prevents any significant heat from escaping at night, resulting in remarkably uniform temperatures across the entire surface of the planet. Interestingly, early astronomers once speculated that Venus might not rotate at all, a puzzle that remained unsolved until the 20th century with the advent of radar technology and space missions like Magellan. The data collected revealed the planet's astonishingly slow and retrograde, or backward, rotation. One of the most compelling theories suggests this strange behavior is the result of tidal interactions with the Sun over billions of years. a process that computer models indicate may have gradually slowed and ultimately reversed its original spin. The extreme length of a Venusian day, combined with its hostile environment, creates substantial technical challenges for any robotic missions sent to its surface. Landers must be engineered to withstand prolonged exposure to crushing pressure and intense heat, all while operating for long stretches without sunlight. This is a primary reason why most studies of Venus are conducted from orbit, providing valuable insights into planetary dynamics and helping you understand how a world so similar to our own in size and mass could have evolved so differently. Shifting our focus to another marvel of our solar system, let's consider Saturn, a planet so light that it could theoretically float, if you could find an ocean vast enough to hold it. Saturn claims the title of the least dense planet in our solar system, with an average density of only about 0.687 grams per cubic centimeter, which is considerably less than that of water. While no such planetary bathtub exists, this analogy perfectly captures the unique physical characteristics of this gas giant. Saturn's remarkably low density is a direct consequence of its composition, as it is made up almost entirely of hydrogen and helium, the two lightest and most abundant elements in the universe. Although the planet is massive, roughly 95 times more so than Earth, these gases are spread across such an enormous volume that the resulting average density seems incredibly low for a celestial body of its scale. Beneath its gaseous atmosphere, scientists believe there may be a small rocky or icy core, but this constitutes only a tiny portion of the planet's total mass. This low density is also closely tied to Saturn's rapid rotation and its distinct shape. The planet completes a full spin on its axis in just over 10 hours, a remarkable speed for such a colossal object. This fast rotation causes Saturn to bulge noticeably at its equator and flatten at its poles, giving it the most pronounced oblate or squashed shape in the solar system. Despite its lightness, Saturn's immense mass generates a powerful gravitational pull. If you could somehow stand on its cloud tops, you would weigh slightly more than you do on Earth. Even when you account for its famous rings, which are composed of countless particles of ice and rocky debris, they contribute very little to the planet's overall mass, leaving it light enough to maintain its theoretical buoyancy. For scientists, density is far more than a curious fact. It serves as a critical tool for understanding a planet's internal structure and formation history. Saturn's low density tells a compelling story of its origins in the frigid, distant regions of our young solar system, a place abundant in light gases and volatile compounds. This finding not only deepens our comprehension of planetary formation, but also offers crucial clues into the birth and evolution of gas giants throughout our galaxy. Within our own solar system, Saturn stands out as a truly unique world, distinguished by its incredibly low density. When you place it alongside the other gas giants, Jupiter, Uranus, and Neptune, it's apparent that each of them is considerably denser, prompting the question of what makes them all so different. Jupiter's greater density, for instance, is a direct result of its immense gravitational pull, which compacts its material to a degree that far surpasses Saturn's. Meanwhile, Uranus and Neptune belong to a completely separate class of planet. Their compositions are abundant in icy materials and heavier chemical elements, which substantially raises their average density compared to Saturn. These worlds are frequently categorized as ice giants, because their internal structure is fundamentally different from the hydrogen and helium makeup of traditional gas giants. Saturn's lightness serves as a powerful illustration that a planet's dimensions and its mass are two very different properties. You might instinctively believe that a massive object must also be heavy. Yet the universe is filled with counterintuitive examples. A planet can expand to a colossal size while staying comparatively light, provided its structure is dominated by low-density substances. To put it in perspective, if an ocean vast enough to contain Saturn existed, the planet would actually float on its surface like an enormous cosmic raft. This makes Saturn the only planet in our solar system with such a distinctive trait, a gigantic sphere composed almost entirely of hydrogen and helium, the lightest elements known. Shifting our focus to the other titan of our system, it's impossible to ignore the spectacular atmospheric events on Jupiter. This planet is a stage for immense storm systems that have been active for hundreds of years, the most renowned of which is the Great Red Spot, a feature that has become Jupiter's defining characteristic. Jupiter's atmosphere is a theater for enormous, unbelievably persistent tempests. The Great Red Spot itself is a formidable anticyclonic vortex, a weather system where atmospheric gases circulate in the opposite direction of a standard cyclone. This storm resides in Jupiter's southern hemisphere and is so vast that you could comfortably fit 2 or perhaps even 3 planets the size of Earth inside it. Astronomers have been observing this feature continuously for more than 4 centuries, dating back to the 1600s. Imagine entire generations of scientists passing while this colossal storm has raged on without pause. The wind speeds inside this vortex regularly surpass 400 kilometers per hour, figures that are almost unbelievable by our terrestrial standards. The sheer endurance and lifespan of Jupiter's storms are profoundly different from anything you would witness on our own planet. Here, storms lose their energy as they interact with continents, oceans, and fluctuating temperature zones. Jupiter, however, lacks any solid surface to disrupt these atmospheric flows, and its massive internal heat constantly feeds and maintains these storm systems for incredible lengths of time. The Great Red Spot is held firmly in place, wedged between 2 powerful jet streams that prevent it from wandering across the planet's face, a configuration that contributes to its extraordinary stability. Although scientists have observed a reduction in the spot's size and intensity over the last few decades, it remains a dynamic system, and researchers cannot yet say for certain if it will eventually vanish or simply transform into something new. More recent investigations have shown that an even more staggering reality lies beneath the visible cloud layers. The storm plunges to tremendous depths within Jupiter's atmosphere, as the Juno spacecraft has detected gravitational irregularities in the area that suggest the Great Red Spot extends hundreds of kilometers downward. This physical depth makes it an astronomically more massive structure than any weather phenomenon ever recorded on Earth. Jupiter's atmosphere is a mixture of hydrogen, helium, ammonia, and numerous other chemical compounds, all supercharged by a potent internal heat source. This energy fuels powerful convective currents, which in turn shape the planet's distinct bands, jet streams, and countless swirling vortices. While some of these smaller storms may merge or break apart, the most massive systems can endure for many years, or even centuries. The vibrant reddish-orange color of the Great Red Spot continues to be a scientific puzzle. One leading hypothesis suggests that the hue is the result of chemical elements like phosphorus or sulfur being altered by the sun's ultraviolet rays. It is believed that different chemical reactions at various altitudes in the atmosphere produce a uniquely layered structure with a rich and varied color palette. Jupiter is also host to other giant storms, including white and brown oval-shaped formations of differing sizes, some of which form when smaller tempests collide and combine. Finally, Jupiter's swift rotation, completing a full spin in less than 10 Earth hours, is a critical factor in shaping its atmosphere. This rapid turning generates powerful Coriolis effects that stretch weather systems into the rotating patterns you see. When you combine this with the planet's immense internal heat, the result is an incredibly dynamic yet remarkably stable global weather system. By studying these storms, scientists can better grasp the fundamental principles that govern the atmospheres of all gas giants, knowledge that is also essential for modeling the conditions on distant exoplanets. Because numerous exoplanets we've found share traits with Jupiter, our own gas giant provides an ideal laboratory for studying extreme atmospheric dynamics and physical events. When you shift your attention to the Saturnian system, you'll discover another remarkable world, the moon Hyperion. This particular object distinguishes itself from countless other moons due to its strange form and completely erratic spin, making it a true celestial anomaly. Measuring approximately 270 kilometers in diameter, Hyperion gives the impression of a massive, misshapen sponge adrift in the cosmos. In contrast to most sizable moons, it has failed to form a sphere, presenting instead an elongated and asymmetrical profile riddled with craters. Many scientists liken its appearance to a cosmic sponge, or perhaps a naturally formed spacecraft of some unknown design, a shape resulting from its low gravity and total absence of geological processes. Hyperion's most incredible characteristic is undoubtedly its utterly chaotic rotation. It behaves completely differently from other moons, which spin in a stable and predictable manner. As Hyperion orbits Saturn, its rotational axis tumbles and shifts at random, a behavior caused by the combination of its irregular shape and the complex gravitational pull from Triton, Saturn's largest moon. This erratic rotation means that Hyperion experiences no regular cycle of day and night. Sunlight bathes different parts of the moon in a completely haphazard sequence, establishing a bizarre and unpredictable lighting environment. The famed Cassini mission confirmed this strange behavior, observing how the moon presented a different face with each pass, and no other moon of its size is known to possess such a chaotic and unstable spin. Hyperion has an incredibly low density, at just 0.55 grams per cubic centimeter, which is less dense than water. This suggests it is composed mostly of water ice with significant empty voids inside its structure, accounting for its porous surface. When meteorites strike, the material doesn't compress easily, creating deep craters with sharp, distinct rims that contribute to its sponge-like look as impact energy fails to spread through its porous body. Interestingly, Hyperion also maintains a slight electrical charge. Data from the Cassini spacecraft revealed that charged particles from Saturn's magnetosphere are interacting with its surface, creating a subtle electrostatic effect. This phenomenon could potentially influence the behavior of cosmic dust near the moon, or even trigger chemical reactions on its surface. Its eccentric and inclined orbit further amplifies its chaotic tumbling, ensuring this instability persists over vast timescales. As one of the few known moons trapped in a state of non-synchronous tumbling, Hyperion is of great scientific value despite lacking an atmosphere, liquid water, or life. It provides researchers with a perfect case study for understanding how irregular shapes and gravitational forces influence the rotation and evolution of celestial objects. This makes it an invaluable natural laboratory for examining complex orbital dynamics and their far-reaching effects. If you journey to the far reaches of our solar system, you'll find that even a remote and frigid dwarf planet like Pluto might conceal incredible secrets under its exterior. Despite its immense distance from the Sun, evidence from the New Horizons mission strongly suggests that Pluto could harbor liquid water beneath its frozen shell. The discovery of features indicating geological activity was a profound surprise for such a small, cold world. Previously, the idea of a subsurface ocean on Pluto seemed extremely improbable, given its surface temperature of around -230 degrees Fahrenheit Celsius, which is cold enough to freeze nearly any substance solid. Yet, telltale signs like cracks, prominent ridges, and resurfaced areas on its crust point to underlying movement. Such activity is likely driven by the pressure of a subterranean ocean pushing up from below. A central piece of this puzzle is Sputnik Planitia, a massive, heart-shaped basin of ice on Pluto's surface. This feature appears to be sinking into the dwarf planet's interior, a behavior that would only be possible if a dense, liquid layer existed underneath. This observation offers compelling evidence that a hidden ocean is indeed present, as the icy crust alone couldn't support such dynamics. The leading theory proposes that heat from the radioactive decay of elements within Pluto's rocky core could be sufficient to maintain water in a liquid state. A thick insulating crust of ice would shield this internal ocean from the extreme cold of space. Located tens or even hundreds of kilometers deep, this ocean might be rich in salts, ammonia, or other antifreeze compounds, further helping it resist freezing in the intense cold. While scientists have not yet made a direct detection of this ocean, they rely on gravitational measurements, surface geology, and thermodynamic models to build their case. Confirming its existence will require future missions equipped with tools for seismological studies or subsurface radar mapping, which could finally provide definitive proof of the liquid world hidden deep beneath Pluto's ice. Pluto is now part of an expanding group of icy worlds, such as the moons Europa, Enceladus, and Triton, which are believed to harbor oceans beneath their surfaces. This suggests that even in the coldest, most remote corners of our solar system, liquid water might be much more prevalent than was once imagined. Such a discovery forces a complete re-evaluation of where habitable conditions could possibly exist within these extreme environments. While an underground ocean on Pluto probably could not sustain life as you understand it, its existence prompts profound scientific inquiries. For instance, what is the potential lifespan of such an ocean, and what kind of interaction does it have with its icy shell? The concept that distant dwarf planets could hide oceans forces us to reconsider the old idea that geological complexity is exclusive to the inner planets, proving that size and solar distance do not rule out internal heat and liquid water. Shifting our focus to Saturn, you are confronted with one of the most enigmatic and visually spectacular phenomena in the solar system. Situated at the planet's north pole is a colossal hexagonal weather pattern, an atmospheric current that perpetually spins around this region. First spotted by the Voyager probes in the 1980s, this incredible formation was later examined in great detail by the long-running Cassini mission, revealing its staggering scale. A width of roughly 30,000 kilometers, which is greater than the entire diameter of Earth. This atmospheric feature has proven to be remarkably stable, enduring across decades of scientific observation. You must realize this is not a solid object on the planet's surface. Instead, it is a dynamic weather system, composed of a geometric arrangement of clouds. The entire structure spins in unison with Saturn's own rotation, holding its position fixed over the pole, with the gases inside moving at over 300 kilometers per hour to form a jet stream that takes on a perfect six-sided shape, instead of a more conventional circular one. The prevailing theory for its existence points to the complex fluid dynamics in Saturn's atmosphere, specifically the interplay between wind currents at varying latitudes. This idea finds support in laboratory simulations, where rotating liquids have formed similar polygonal patterns. Nevertheless, the immense size and unwavering persistence of Saturn's hexagon remain an unsolved scientific puzzle, as the formation's shape does not morph or vanish, and has shown no signs of weakening over more than a decade of observation by Cassini. Infrared imaging shows that this is not merely a surface-level event. The hexagon is a multi-layered formation that extends deep into the atmosphere, potentially for hundreds of kilometers. This points to a structure that is profoundly embedded within the planet's overall atmospheric system. Right in the middle of this hexagon, you find a massive storm fixed over the North Pole, complete with an eye and spiral bands that bring to mind hurricanes on our own world, though it operates independently of the larger hexagonal structure. What makes this feature even more perplexing is the complete lack of a similar hexagon at Saturn's south pole, which instead hosts a more typical, circular, hurricane-like vortex. This asymmetry between the poles deepens the mystery, and might be linked to disparities in solar heating or internal atmospheric processes. While some theories propose standing waves as a cause for the geometric pattern, no current model can successfully replicate the sheer scale, depth, and endurance of the actual hexagon on Saturn. This hexagon stands as one of the most bizarre and unexplained phenomena within our solar system. Scientists are still sifting through archival data from the Cassini mission for further clues, while future explorations could offer superior data on its wind speeds, temperatures, and chemical makeup. For the time being, Saturn's northern hexagon serves as a stunning case of natural geometric order, formed not from rock or ice, but from the dynamic motion of massive gas clouds, driven by forces we have yet to comprehend. As we conclude this exploration of the outer solar system's wonders, you encounter one of the most extraordinary processes theorized to happen deep inside the gas giants. Scientific models suggest that on planets like Neptune and Uranus, it literally rains diamonds. This spectacular event is thought to be a result of the immense pressures within the atmospheres of these ice giants, which are abundant in hydrocarbons like methane, a key source of carbon, the essential element for diamond formation. Deep inside these distant worlds, the pressure builds to a level millions of times more intense than what you experience from Earth's atmosphere. At these profound depths, the sheer force is enough to shatter and reconfigure the atomic structure of carbon, compelling it to recrystallize into diamonds. Scientists theorize that a precise combination of heat and pressure causes methane molecules to break apart, allowing the liberated carbon atoms to lock into the crystalline structure of solid diamonds, which then slowly descend through the planet's interior under the pull of gravity. This incredible phenomenon is believed to start around 1,000 kilometers below the visible cloud tops of these planets. Diamond rain doesn't happen in the upper atmosphere, but originates far deeper, where the conditions are severe enough to force carbon into its crystalline form. You won't find such extremes in traditional gas giants like Jupiter or Saturn, as their compositions are dominated by hydrogen and helium, lacking the necessary abundance of carbon compounds for this process to occur. The concept of diamond rain first emerged in the 1970s, but it wasn't until modern lab experiments that it captured significant scientific interest. Using high-powered laser facilities, researchers have managed to replicate the conditions found deep within Neptune and Uranus. In these simulations, they successfully subjected hydrocarbons to immense pressure and heat, compelling them to form tiny diamond crystals and lending strong support to the theory. It's doubtful that the diamonds produced in these planets remain solid forever. As they sink into even deeper and hotter regions, they likely melt into a liquid state, or dissolve entirely into other fluid layers of the planetary core. However, the formation of these diamonds could be an ongoing cycle, playing a crucial role in the internal heating and energy circulation of these ice giants. This process might also clarify why the internal heat radiating from Uranus and Neptune is considerably lower than that of Jupiter and Saturn. It's possible the act of diamond formation traps energy within the planet, or alternatively, the friction generated by the falling diamond crystals could add to the heating of the inner layers. While the exact mechanics are a subject of ongoing research, the prospect of harvesting these diamonds is completely out of the question, as they are forged in an intensely hostile environment. The idea itself is backed by solid scientific evidence, illustrating just how bizarre and extreme chemical reactions can become in the far reaches of our solar system. The interior conditions of these planets are so alien that we are only just scratching the surface of the incredible events taking place beneath their clouds. In fact, some scientists even theorize that vast oceans of liquid diamond might exist in the deepest regions of Neptune and Uranus, though this remains a speculative concept for now. Uranus and Neptune continue to be the most mysterious planets in our cosmic neighborhood, primarily because no spacecraft has ever orbited them for extended study. Consequently, much of what we know comes from the brief Voyager 2 flyby mission, supplemented by observations from Earth-based and space telescopes. Future missions, equipped with more sophisticated instruments, might one day be able to verify the diamond formation process up close. Contemplating these astounding discoveries helps you appreciate that our solar system is brimming with breathtaking wonders and unanswered questions. From the fact that Saturn could float in water, to the diamond showers on ice giants, every celestial body offers unique features that captivate and motivate scientists across the globe. Fantastical events are unfolding in the depths of our planetary neighbors, forcing us to redefine our understanding of what constitutes normal weather. Just picture it. Deep inside Uranus and Neptune, immense pressure is actively squeezing carbon into brilliant crystals that drift down through the planetary layers like a sparkling diamond rain. These remote ice giants present you with some of the most extraordinary and exotic atmospheric phenomena in the solar system. Speaking of harsh environments, our closest neighbor, Venus, immediately comes to mind. Its atmosphere is so punishingly dense and corrosive that any lander sent to its surface survives for only a few minutes before the staggering pressure crushes it completely. The atmosphere of Venus is a technological nightmare, representing one of the most hostile environments of any known planet. It is composed almost entirely of carbon dioxide, and is shrouded in thick, swirling clouds of concentrated sulfuric acid. At the surface, the atmospheric pressure is 92 times greater than Earth's, which is comparable to the pressure you would feel almost a full kilometer beneath the ocean. This force is powerful enough to instantly flatten nearly any spacecraft. The history of Venus exploration is a chronicle of both incredible achievements and heartbreaking failures, as several ambitious missions have attempted to conquer its surface. The only true successes in this monumental challenge were the Soviet Union's Venera automated landers during the 1970s and 1980s. These remarkable probes not only made it to the planet's blistering surface, but also managed to send back vital scientific information. These resilient machines set records for survival in an inferno, with the longest-lasting probe functioning for nearly 2 hours before succumbing to the environment. Most of the other landers were destroyed by the crushing pressure and intense heat in under an hour. The temperature on the Venusian surface is almost beyond comprehension, reaching a staggering 465 degrees Celsius, or 865 degrees Fahrenheit, 169 degrees Fahrenheit. What makes this extreme heat truly remarkable is that Venus is even hotter than Mercury, a planet that is significantly closer to our Sun. Despite receiving less direct solar radiation, Venus's thick, dense atmosphere creates an extreme greenhouse effect. This runaway process traps heat so effectively that it has turned the planet's surface into a scorching, uninhabitable wasteland. This extreme environment establishes Venus as the most scorching planet within our solar system. In such blistering conditions, all electronic components and materials inevitably fail, being obliterated in a matter of minutes. The planet's thick atmosphere presents issues far beyond immense pressure. It dramatically alters the way a spacecraft descends. You have to picture parachute systems being effective only in the upper atmosphere, after which a probe must literally sink through a dense soup, its fall slowed to a crawl by overwhelming air resistance. Upon finally reaching the surface, any lander confronts a truly infernal reality. The searing heat works in tandem with aggressive, corrosive chemicals that systematically corrode every instrument and system. High above, at an altitude of about 50 kilometers, clouds of sulfuric acid start to form. While the temperatures at these heights are slightly more manageable, the acidity of the air is so extreme that it poses a lethal danger to any sensors or optical equipment. Consequently, any mission designed to explore Venus requires multiple layers of defense against both chemical erosion and thermal annihilation, presenting an incredibly demanding engineering challenge. All landers sent to Venus must be equipped with exceptionally dense shielding and high-capacity cooling systems. These necessary additions, however, drastically increase the probe's mass, which makes dispatching complex scientific payloads extraordinarily difficult. This is why a majority of modern missions opt for orbital surveys or employ high-altitude balloons to bypass the most hostile atmospheric layers. Upcoming research initiatives, including NASA's Veritas mission and the Da Vinci Project, are set to investigate this enigmatic planet more thoroughly and safely. The Da Vinci probe is designed to plunge through the atmosphere, taking continuous measurements of temperature, pressure, and chemical makeup. Although it is not expected to survive impact with the surface, the information it gathers during its descent will be of immeasurable scientific importance. There are also exciting proposals to create high-temperature electronics based on materials like silicon carbide that could theoretically operate for hours or even days on the Venusian surface, though this technology remains in active development. You'll find that Venus shares a remarkable similarity in size with Earth, yet its environment is the absolute antithesis of our own world. The oppressive atmosphere not only generates crushing pressure, but also obstructs all visible light, rendering visual observation of the surface from orbit virtually impossible. To chart the detailed topography of Venus, scientists are compelled to employ sophisticated radar mapping techniques. In essence, Venus annihilates most spacecraft in mere minutes because of its combination of extreme pressure, intolerable heat, and corrosive acidity, making it one of the most inhospitable locations for technology in the solar system. while simultaneously being one of the most scientifically valuable objects for us to study. A completely different, yet equally fantastical world is presented by Titan, Saturn's largest moon. On this incredible satellite, you can find fully formed rivers, stunning lakes, and periodic rains, all composed not of familiar water, but of liquid methane. Titan is, in fact, the most massive natural satellite in the Saturnian system, with a surface that is extensively carved by a network of rivers, lakes, and even vast seas, all filled with liquid methane and ethane instead of water. In the extremely frigid conditions on Titan, methane behaves almost exactly as water does on Earth. It evaporates, ascends into the atmosphere, condenses into clouds, and then precipitates as rain, creating a complete methane-based hydrological cycle. This moon experiences distinct seasons, with its weather patterns shifting over time. Researchers have even documented the development of storm systems and rainfall in different regions, corresponding to the changing seasons, while dark streaks seen on the surface provide compelling evidence of recent, heavy downpours. Radar imagery reveals that most of these lakes are clustered near the polar regions, particularly around the North Pole, and the sheer scale of some of these methane bodies is truly staggering. One of the most remarkable features is a sea named Kraken Mare, a colossal expanse of liquid methane, larger than all of North America's Great Lakes combined. Data from the Cassini spacecraft indicated that in certain areas, this sea is at least 300 meters deep. Scientists have also uncovered strong evidence of wave activity in these methane seas, and have even observed islands that appear and vanish, likely due to masses of drifting ice. Despite its alien composition, Titan is one of the most Earth-like worlds ever discovered, when you consider its landforms and surface processes. You can observe valleys etched by flowing liquid, intricate drainage networks, and even features that look like river deltas. But all this geologic activity unfolds in a much colder setting, where methane assumes the role of water. The surface temperature hovers around -179 degrees Celsius, a cold so intense that ordinary water ice is as hard as rock, allowing methane to exist as a flowing liquid. Titan's dense atmosphere, which is composed primarily of nitrogen, is even thicker than our own, meaning it supports genuine weather phenomena, including winds and cloud formations. Researchers have even identified dunes sculpted by these winds. Furthermore, the Cassini probe detected events similar to lightning discharges, pointing to the existence of atmospheric electricity interacting with the organic molecules present in the atmosphere, making Titan one of the most chemically fascinating and complex locations in our entire solar system. A great number of scientists propose that Titan may be hosting prebiotic chemical reactions, transforming it into an ideal natural laboratory for you to examine the circumstances that could potentially give rise to life. A dense haze of complex hydrocarbon compounds gives Titan's atmosphere its signature orange color. This atmospheric smog is so thick that it completely conceals the moon's surface from view in the visible light spectrum, which is why the Cassini probe had to rely on radar systems to create its maps. An exciting mission named Dragonfly is on the horizon, with a planned launch in 2028, which will dispatch a specialized drone to explore Titan's surface from the air. Furthermore, Titan exhibits strong indications of a subsurface ocean concealed beneath its frozen crust, a body of liquid water likely blended with ammonia. Should this ocean's existence be confirmed, it would mean Titan offers a second potential habitat for life, one centered around methane on its surface, and another based on water far below. Titan stands as the only moon in our solar system known to have stable bodies of liquid on its surface. This combination of a substantial atmosphere, intricate liquid cycles, and rich chemical environment makes it a truly unparalleled object and a top priority for all future scientific inquiry, as researchers aim to unravel the mysteries of both planetary evolution and the fundamental ingredients for life. Now, let's explore an even more fascinating phenomenon concerning Mercury, the smallest planet in our solar system, which is slowly but surely contracting over time. For billions of years, Mercury has been gradually shrinking as its interior cools down. The planet's core constitutes the majority of its volume, and as this core sheds heat, it solidifies and reduces in size. This internal contraction compels the planet's outer layers to compress and wrinkle, which in turn forms distinctive cliffs and mountain ranges across its surface. These geological features, known as lobate scarps, can extend for hundreds of kilometers and rise to heights of several kilometers. They are plainly visible from space and offer a dramatic illustration of how the planet's crust has been squeezed and buckled, serving as undeniable proof that the planet is indeed getting smaller. From a geological standpoint, some of these formations appear quite recent, suggesting that Mercury's contraction might still be an ongoing process today. The total decrease in the planet's diameter is estimated to be around 7 kilometers throughout its history, and while that may sound minor on a planetary scale, such a shift results in massive surface deformations. The process of contraction on Mercury is slow, yet continuous. Unlike Earth, Mercury has no tectonic plates, so this shrinkage happens in a more direct and uniform way. The planet's core is exceptionally large for its size, making up about 85% of its radius. As this core cools and contracts, it effectively tugs the crust inward, fracturing the surface and creating enormous step-like structures that give the impression of the ground folding in on itself. Because Mercury has almost no atmosphere to speak of, these features are perfectly preserved. There is no erosion, weather, or tectonic activity to smooth them over, allowing the scarps to remain as timeless markers of the planet's evolution. In some of the high-resolution images captured by spacecraft, you can observe smaller scarps cutting across more recent impact craters, which signifies that the contraction continued even after those craters were formed, providing further evidence that the process is still active. The planet's close orbit to the Sun subjects its surface to immense thermal stress. The temperature swings are dramatic, from minus 170 degrees Celsius at night to a scorching plus 430 degrees during the day. This extreme cycle forces the crust to expand and contract repeatedly, adding to the strain and deformation of the rock over geological time. While we see no indications of active volcanoes on Mercury today, many of its vast basins are unmistakably volcanic in origin, which supports the theory that its interior was once exceptionally hot and geologically dynamic. After the planet radiated away most of its internal heat, contraction took over as the principal force shaping its geology. This process is a global phenomenon, and unlike Mars, which became geologically inert early on, Mercury continues to display subtle but persistent signs of internal evolution. Finally, let's consider our own natural satellite, the Moon, which is gradually but consistently receding from the Earth. Each year, the Moon drifts approximately 3.8 centimeters farther away from our planet. This measurement has been confirmed with incredible accuracy using laser reflectors that were placed on the lunar surface by the crews of the Apollo missions. The reason for this steady departure is found in the tidal interactions between our two celestial bodies. Earth's gravity exerts a pull on the Moon, and in return, the Moon's gravity influences Earth's oceans, generating the tides. This tidal friction gradually transfers Earth's rotational energy to the Moon, causing it to accelerate slightly in its orbit and slowly spiral away from us. Simultaneously, this energy transfer causes Earth's rotation to decelerate, which means that our days are gradually becoming longer. In our planet's remote past, billions of years ago, a single day was much shorter than it is now. You can imagine a time when a day lasted only a few hours, and a colossal, silvery moon dominated the sky, appearing much larger than the one we are accustomed to today. This cosmic dance continues, though the changes are so gradual that they are imperceptible over a human lifetime. If we project this process into the distant future, scientific models paint a remarkable picture where a day on Earth could extend to 25 hours or even longer. A staggering thought, but a natural outcome of a process that has been underway for eons. Each day, our planet's rotation slows by an infinitesimal amount, just as the Moon drifts a few centimeters farther from us every year. Yet our satellite's impact goes well beyond merely marking the passage of time. The Moon serves as a crucial cosmic gyroscope for Earth's axial tilt, and its gravitational pull prevents our world from tumbling erratically through space. This stabilizing effect is what has allowed for a relatively consistent climate across vast geological ages. Consider for a moment what might occur if the Moon were to vanish or be significantly more distant. Earth's axis could begin to wobble dramatically, triggering catastrophic climate shifts that would completely reshape the landscape of life on our planet. While such tidal forces are present elsewhere in the universe, the relationship between Earth and its Moon is unique. Our satellite is extraordinarily large in comparison to its host planet, which results in the powerful ocean tides and the long-term rotational changes that we can observe today. Over the course of billions of years, this mutual gravitational pull has profoundly transformed the Earth-Moon system. In the distant past, our Moon orbited much more rapidly and was a hotbed of geological activity, its surface a canvas of volcanoes and lava flows sculpted by immense internal heat. What we see today is a stark contrast, a frozen, silent world that perpetually presents the same hemisphere to us. This phenomenon, known as tidal locking, arises from a complex gravitational resonance that gradually synchronized the Moon's spin with its orbit. Theoretically, this gravitational dance could progress even further into a state scientists refer to as tidal equilibrium. In such a scenario, both Earth and the Moon would be locked in place, constantly facing each other, and a day on Earth would last as long as a lunar month. You could imagine a world where a colossal moon is a permanent fixture in the sky for one half of the planet, while remaining forever unseen by the other. However, achieving this state would take tens of billions of years, far longer than the remaining lifespan of our Sun. Even though these changes are incredibly slow, their cumulative impact is staggering. Since its formation, the Moon has already receded by tens of thousands of kilometers, a shift that has influenced nearly everything, from the speed of Earth's spin to the nature of solar eclipses. The reason modern solar eclipses appear as they do, with the Moon almost perfectly obscuring the solar disk, is a direct consequence of its current distance from us. The moon's gradual retreat is actually one of the most precisely measured long-term phenomena in our entire solar system. Using laser reflectors left behind by the Apollo astronauts, scientists can track the distance to the moon with millimeter accuracy. This information is invaluable not only for comprehending our own planetary system, but also for modeling the dynamics of exoplanets in other star systems. Studying our moon's behavior provides a unique window into the orbital mechanics governing distant worlds. Every new insight into the moon's evolution deepens our understanding of how planetary systems form and develop across the cosmos. While its drift is imperceptible in our daily lives, over eons, it fundamentally alters our world's tides, rotation, and even the appearance of our night sky. This constant, subtle motion helped create the very conditions for life to emerge and thrive, and we are still uncovering the full extent of its consequences. Let's now shift our focus to the behemoth of our solar system, Jupiter, which boasts the most powerful magnetic field of any planet in our cosmic neighborhood, a field approximately 20,000 times stronger than Earth's. Picture an invisible force with enough power to ensnare charged particles from the solar wind, accelerating them to incredible speeds. These particles become trapped, forming intense radiation belts that envelop the gas giant. The radiation surrounding Jupiter is so potent that it can incapacitate the electronics of an unshielded spacecraft in a matter of hours. Consequently, any mission sent to explore this world demands specialized radiation hardening to protect its scientific instruments from being rendered useless. This presents a formidable engineering obstacle for anyone wishing to study the planet up close. Jupiter's immense magnetic field stretches for millions of kilometers into space, creating a vast structure known as the magnetosphere. This invisible bubble of influence is so large that it completely encloses the orbits of several of Jupiter's largest moons. These celestial bodies are therefore constantly immersed in streams of charged particles, leading to complex electromagnetic interactions with their host planet. Io, one of Jupiter's most dynamic moons, serves as a spectacular example of these forces at play. As Io carves its path through the planet's magnetic field, it generates an electrical current measuring in the millions of amperes. This interaction not only produces breathtaking auroras at Jupiter's poles, but also fuels the plasma clouds that surround the gas giant. Simultaneously, Io endures a relentless barrage of charged particles that continually reshapes its surface and its tenuous atmosphere. Europa, another of Jupiter's celebrated moons, is also profoundly affected by the magnetic field. As the field lines sweep across its icy crust, they are thought to induce electrical currents within a hidden subsurface ocean. In fact, it was this magnetic data that provided scientists with convincing evidence for the existence of liquid water beneath the frozen shell. The salty, conductive properties of this ocean make Europa one of the most compelling locations in our search for life beyond Earth. Among all the moons in our solar system, Ganymede stands alone, distinguished by the fact that it generates its own magnetic field. This personal magnetosphere engages directly with Jupiter's colossal field, giving rise to intricate areas of magnetic reconnection. These interactions can trigger shifts in auroral displays and alter the space environment immediately surrounding Ganymede. And by observing them, we gain deeper insights into the fundamental physics of magnetic fields across the cosmos. The sheer strength of Jupiter's magnetic field transforms the area around the planet into an extremely hazardous environment for any spacecraft. Missions like Galileo and Juno demanded extraordinarily careful flight path calculations to limit exposure to the most intense radiation belts. Proximity to the gas giant exposes equipment to radiation so powerful it can obliterate unprotected instruments in a matter of hours, if not minutes. Jupiter's magnetosphere acts as a formidable shield, redirecting the bulk of the solar wind away from its moons. Yet, it also traps particles that accelerate to incredibly high energies, effectively creating a source of localized cosmic rays. This entrapped radiation is a key factor in sculpting the surfaces of the inner moons, capable of stripping away their tenuous atmospheres and changing the very chemistry of the materials on their ground. The magnetic field's immense power is also responsible for producing powerful radio emissions that we can pick up from Earth with radio telescopes. The characteristics of these radio signals fluctuate in response to Jupiter's spin and the orbital positions of its major moons. In fact, these Jovian radio signals were one of the earliest cosmic phenomena identified by pioneers in radio astronomy, and they remain a vital source of information about the dynamics inside its magnetosphere. The source of Jupiter's magnetic field is fundamentally different from Earth's, which arises from a solid iron core. Deep inside the gas giant, immense pressures transform hydrogen into a liquid metallic state, allowing it to conduct electricity. This, combined with Jupiter's incredibly swift rotation, a day lasts less than 10 hours, supercharges the dynamo effect, generating a magnetic field that is both vast and incredibly intricate. The magnetic environment around Jupiter governs every object within its reach, from the smallest flecks of cosmic dust to moons as large as planets. Consequently, any future expedition to the Jovian system must treat this magnetic field as a critical element in every stage of planning. This isn't merely a powerful field. It represents one of the most dominant and formative forces in our whole solar system. Let's now shift our focus to the fringes of our planetary system, where we find the enigmatic Triton, Neptune's largest satellite. What makes Triton so fascinating is its retrograde orbit, meaning it circles its planet in the reverse direction of Neptune's own rotation. This trait sets it apart from nearly every other major moon in the solar system, almost all of which travel in the same direction as their planets spin. This peculiar motion is a strong indicator that Triton is not a native moon that formed alongside Neptune. The prevailing scientific theory is that it was an object from the outer solar system, captured by the planet's gravitational field. It's plausible that Triton was originally one half of a binary pair of Kuiper Belt objects that strayed too near Neptune, resulting in a gravitational exchange that flung its partner into deep space, while leaving Triton ensnared. Triton is remarkably large, surpassing Pluto in size and standing as one of the most substantial bodies in the outer solar system. Snaring an object of this magnitude would have been a monumental event in our system's history. Following its capture, Triton would have been locked in a highly eccentric and unstable orbit, which over millions of years was gradually circularized by gravitational forces, all while its backward orbital direction remained. Its backward journey around Neptune generates persistent tidal stresses between the two bodies, which are steadily causing the moon's orbit to decay. Far into the future, Triton is destined to drift so close to Neptune that it will cross the threshold where the planet's immense tidal forces will rip it to pieces. The resulting debris would then likely settle into a magnificent new set of rings around Neptune, potentially rivaling or even exceeding the complexity and beauty of Saturn's. Triton boasts a host of other incredible characteristics, including one of the coldest surfaces known, with temperatures plummeting to around -235 degrees Celsius. This frigid landscape is coated in nitrogen ice, which lends it a distinct pinkish color. Remarkably, despite this profound cold, Triton displays clear evidence of geological activity, a feature quite unexpected for a world so far from the Sun. Data from the Voyager 2 spacecraft revealed the existence of cryovolcanoes on Triton's surface. These are not volcanoes in the traditional sense. Instead of molten rock, they spew out a slurry of water ice, nitrogen, and other volatile compounds. This points to an internal source of heat, most probably generated by the constant tidal friction from its gravitational dance with Neptune, which deforms Triton's interior and fuels its geological engine. By cosmic timelines, Triton's surface is surprisingly youthful, as indicated by a scarcity of impact craters that points to recent geological resurfacing. The Voyager 2 probe even captured images of nitrogen geysers erupting, launching plumes of gas and dust several kilometers into the sky. This is undeniable proof that Triton's surface is not static, but continues to be reshaped in the present day. Triton also possesses a tenuous atmosphere, made up mostly of nitrogen, that experiences seasonal shifts as its orbit carries it through varying levels of solar heating. These changes cause the atmospheric pressure to fluctuate, which in turn can drive surface processes like the sublimation and refrosting of nitrogen ice. While far too thin to enable flight, this atmosphere is significant enough to contribute to surface erosion and the movement of materials across the landscape. Because of its unique orbital path and its specific chemical makeup, Triton is frequently likened to Kuiper Belt objects such as Pluto. This strong resemblance lends considerable weight to the theory that it originated in that distant, icy realm before being captured by Neptune. The acquisition of such a massive object provides a compelling explanation for the eclectic collection of Neptune's moons, and serves as a testament to the turbulent, dynamic nature of the early solar system. Voyager 2, which flew past the Neptunian system in 1989, stands as the sole probe to have ever visited. The invaluable images and data it gathered remain our primary wellspring of knowledge about Triton, leading scientists to designate this enigmatic world as a high-priority destination for future exploratory missions because of its distinct origins, geological activity, and its potential as an analog for other bodies in the outer solar system. Let's now tackle one of the most persistent misunderstandings concerning our solar system: the notion that the asteroid belt is a jam-packed field of stones and cosmic rubble. The truth is, the asteroid belt, situated between the orbital paths of Mars and Jupiter, is overwhelmingly comprised of empty space. Individual asteroids are separated by immense gaps, often millions of kilometers wide, making the likelihood of a collision exceptionally low. In fact, if you were to travel on a spacecraft through this region, you would almost certainly fail to spot a single asteroid with your unaided eye. The entire mass of all the asteroids combined amounts to less than 5% of our moon's mass, which underscores their sparse distribution. Even Ceres, the largest object in the belt, measures only about 950 kilometers in diameter. Other prominent bodies like Vesta and Pallas are considerably smaller, and the overwhelming majority of asteroids are nothing more than minuscule rock fragments, scattered far and wide. Contrary to a common belief, these remnants are not the rubble from a shattered planet. Instead, they represent primordial matter that was prevented from ever consolidating into a planet by the immense gravitational pull of Jupiter. The gas giant's powerful gravity perpetually unsettled the orbits of objects in this zone, not only stopping them from merging, but also triggering collisions that broke down larger bodies into the smaller pieces we see today. The belt is home to hundreds of thousands of documented asteroids, with millions more smaller objects likely yet to be discovered. Despite these seemingly large numbers, the volume of space they inhabit is so vast that the region remains profoundly empty. If you were to stand upon the surface of one asteroid, you would almost certainly need a telescope to catch a glimpse of another. This main belt spans an area from roughly 2.1 to 3.3 astronomical units from the Sun, encompassing a region larger than 100 million square kilometers. Consequently, the cinematic idea of a spacecraft expertly weaving through a dense field of asteroids is pure fantasy. The actual density of objects in the belt is so minimal that modern interplanetary missions can traverse it without requiring any special evasive maneuvers. Indeed, rather than viewing it as a hazard, many missions to the outer planets have leveraged the journey through the belt as a valuable opportunity for conducting additional scientific studies. Asteroids exhibit a wide range of compositions, which is tied to where they originated in the primordial solar system. Some consist mainly of rock and metal, whereas others are heavily composed of carbon-based compounds. These compositional variations offer scientists crucial clues about the mechanisms of planet formation and the broader evolutionary history of our cosmic neighborhood. Research endeavors such as the Dawn mission, which explored Vesta and Ceres, and the OSIRIS-REx and Hayabusa 2 missions, which successfully brought asteroid samples back to Earth, have dramatically deepened our understanding of these ancient celestial bodies. The asteroid belt also features what are known as asteroid families, collections of objects sharing similar orbital paths and makeups, which are understood to be the debris from larger parent bodies. The presence of these families confirms that significant collisions did take place in the distant past, though in the current epoch, the belt is a predominantly serene and stable environment. Looking to the future, some asteroids are viewed as potential sources of resources for space missions, possibly containing rare metals, water, and other materials that are costly to launch from Earth. However, actually harvesting these resources would mean confronting the enormous logistical challenge of navigating the vast empty distances between them. Ultimately, the asteroid belt is not a chaotic mess of wreckage, but a structured and relatively calm region of widely scattered objects. Its surprising emptiness is precisely what has allowed spacecraft to cross it safely on numerous occasions, paving the way for the exploration of our system's outer planets. This reality connects directly to the captivating theory of a failed planet between Mars and Jupiter, an idea that has long fascinated both scientists and space enthusiasts. Such a hypothetical world could account for the belt's existence and other structural details of the inner solar system, with researchers proposing that planetary accretion was indeed underway here, before Jupiter's powerful gravity brought the process to a premature halt. The total mass of all the asteroids in the belt today is merely a small fraction of what would be needed to construct a complete planet. This deficit strongly implies that a huge amount of the original material was either flung out of the solar system or assimilated by other celestial bodies. While this region may have once held sufficient building blocks for a planet, the constant gravitational disturbances from Jupiter rendered orbits too unstable, causing collisions to shatter any fledgling attempts at large-scale formation. The existence of asteroid families, groups of fragments from once larger bodies, lends weight to this hypothesis. It is possible that some of these fragments are the leftover cores or mantelpieces of protoplanets that started to form but were ultimately destroyed before they could fully mature, suggesting that at least partial planet formation occurred here. One of the more dramatic theories posits that a single large protoplanet did manage to form, but was subsequently obliterated by a catastrophic impact. Current evidence, however, does not convincingly support the scenario of a single massive shattered world. Instead, the data points toward a long history of sustained gravitational disruption, a model that aligns better with the idea of an interrupted planetary formation process, a story that the diverse types of asteroids in the belt continue to tell. The presence of carbonaceous C-type, silicate I-type, S-type, and metallic M-type asteroids demonstrates that materials from various regions of the nascent solar system became intermingled here. This cosmic boneyard holds pristine samples of primordial matter, offering clues about what could have evolved into a planet if conditions had been different. Jupiter's influence in halting planet formation within the asteroid belt was absolutely critical. Its immense gravitational pull established orbital resonances, which in turn created zones of instability and cleared out specific areas in the distribution of asteroids. These resonant zones, which you may know as the Kirkwood gaps, either flung material out of particular orbits or caused objects to smash into each other at tremendous speeds, thereby preventing their accretion into a larger body. Ceres, the most massive object in the asteroid belt and classified as a dwarf planet, serves as the best example of what might have developed into a full-fledged planet under more favorable circumstances. Yet, even Ceres is minuscule compared to actual planets, highlighting just how effective Jupiter's gravitational interference truly was. In earlier times, scientists put forward theories about a hypothetical planet named Phaeton, which was thought to have been obliterated, its fragments forming the asteroid belt. However, the modern scientific consensus does not endorse the concept of a single shattered planet. Instead, all available evidence supports the model of an interrupted process of planetary formation, meaning today's asteroid belt is not the wreckage of a former world, but the unfulfilled potential of one that never finished forming. Now, let's shift our focus to the truly remarkable system of Uranus, where you'll find moons orbiting in a profoundly inclined plane, making it seem as if the entire planetary arrangement has been knocked over. Uranus possesses an extraordinary axial tilt of approximately 98 degrees, which means the planet is essentially orbiting the Sun on its side. This characteristic makes it entirely unique among the planets in our solar system, as no other body shares such an extreme orientation. The most widely accepted explanation for this bizarre positioning attributes it to a colossal impact early in the planet's formation. A theoretical impactor, possibly the size of Earth or even larger, could have struck Uranus with enough force to drastically alter its rotational axis without completely destroying the planet. This cataclysmic encounter didn't just tip the planet over, it also profoundly shaped the development of its entire system of moons. As a consequence of this tilt, there are periods in Uranus's orbit when its poles point almost directly toward the Sun, leading to extreme seasonal variations that each last for more than 20 Earth years. During the summer on Uranus, one of its poles is bathed in unending sunlight, while the other hemisphere is cast into a continuous, decades-long polar night. The planet's moons, including its largest, Titania, Oberon, Ariel, Umbriel, and Miranda, all conform to this tilted orientation, circling the planet along its angled equatorial plane. When you view it relative to the rest of the solar system, the entire Uranian system appears to have been tipped onto its side. This peculiar alignment governs how sunlight strikes the moons as they orbit, resulting in prolonged periods of light and shadow that can extend for decades at a time. Miranda, one of the smallest of Uranus's major moons, possesses one of the most enigmatic surfaces discovered anywhere in the solar system. Its landscape is a bewildering collage of immense cliffs, jumbled geological features, and strange formations that seem to defy all known geological processes. Some of these sheer cliffs are estimated to be up to 20 kilometers high, making them several times taller than Mount Everest. Scientists theorize that Miranda may have been shattered by a tremendous impact and then haphazardly pulled back together by its own gravity. This reconstruction could be connected to the very same catastrophic event that tilted Uranus itself, with the moon's varied terrain possibly representing jumbled fragments from different layers of the original body. Even Uranus's magnetic field bears the marks of a violent past. It is inclined at an angle of nearly 60 degrees relative to the planet's rotational axis, and is also significantly displaced from its geometric center. This highly unusual setup is fundamentally different from the more orderly magnetic fields of other planets, and may well be another consequence of the ancient collision. Although the internal structure of Uranus is not well understood, the off-center magnetic field might suggest a stratified interior or a displaced core. Collectively, these characteristics make Uranus one of the most asymmetrical and mysterious planets in our solar system. And by studying these anomalies, we gain a deeper understanding of the extreme events that may have shaped the early solar system. To this day, Voyager 2 is the only spacecraft to have visited the Uranian system, having performed a flyby of the planet back in 1986. The information it gathered still provides the cornerstone of our knowledge, but many details remain obscured due to the brief observation window and the immense distance. Future missions could dramatically expand our insights into the composition of its moons, the dynamics of its atmosphere, and the planet's internal structure. The orbits of Uranus's moons are situated relatively close to the planet, creating a tightly packed system. Because they follow the planet's tilted equatorial plane, their paths look highly peculiar from the perspective of the solar system's main orbital plane. Instead of moving in a familiar horizontal pattern, the moons appear to travel almost vertically, a unique configuration not seen anywhere else in our planetary neighborhood. Some theoretical models even propose that prior to the devastating collision, Uranus might have possessed a more substantial ring system that was obliterated by the impact. The planet's modern rings, which are faint, narrow, and made of dark material, could be the lingering remnants of that original, grander system. Just try to picture the magnitude of such an event. A body the size of our own planet, or possibly even larger, collided with a young Uranus, knocking it completely onto its side and giving rise to the distinct arrangement we see in the present day. This impact theory neatly accounts for the planet's peculiar axial tilt, its bizarre seasons, its magnetic irregularities, and the orbital paths of its moons. The fact that its moons are aligned with the new rotational axis further bolsters the idea that they formed from the wreckage of this cosmic collision, showcasing just how violent and unpredictable the birth of planetary systems could be. Studying an extreme case like Uranus helps you grasp the full range of possibilities in planetary evolution and broadens your understanding of the sheer diversity of systems in the cosmos. This distant ice giant and its moons stand as a striking testament to how a single, cataclysmic event can fundamentally reshape an entire planetary system. When you examine this world, you are looking at the aftermath of a cosmic disaster whose repercussions are still evident today. Your solar system is engaged in a perpetual, immense voyage around the heart of the Milky Way, a cosmic circuit that requires between 225 and 250 million years to complete. To put that duration into perspective, the dinosaurs had not yet begun to roam the Earth the last time our system occupied its current galactic coordinates. This recurring journey is termed a galactic year, and throughout its entire existence, our solar system has finished this lap only about 20 times. The velocity of our journey is nothing short of astonishing, as we hurtle through space at an average speed of approximately 828,000 kilometers per hour. Despite this incredible pace, the sheer scale of our galaxy makes the trip exceptionally long. The Milky Way itself measures 100,000 light-years across, and our solar system resides about 27,000 light-years away from its core, nestled inside one of the galactic spiral arms. It's crucial to realize that our path around the galactic center is not a perfect circle. It is slightly elongated and involves vertical fluctuations that carry the solar system above and below the galactic plane. These oscillations happen approximately every 30 to 40 million years. Some scientists have even proposed a potential link between these galactic movements and the cyclical mass extinctions that have occurred on Earth, though definitive proof for this theory is still missing. The gravitational pull that locks our solar system into its orbit has a multifaceted source. While a supermassive black hole at the galaxy's core generates a potent gravitational field, it's actually dark matter that plays the most significant role. This unseen substance constitutes the majority of the galaxy's mass, and is the essential glue that binds the spiral arms and all their star systems into one cohesive structure. This galactic trek is not a solitary one. We are constantly subject to the gravitational effects of nearby stars and interstellar gas clouds. Although these forces are too weak to disturb the planets in our system, they can influence objects in the far-off Oort cloud, sometimes sending comets on a path toward the inner solar system. As we move in relation to other galactic structures, the very appearance of our night sky slowly transforms, meaning the constellations you see today are temporary and will be unrecognizable millions of years in the future. Even though the galaxy is filled with countless stars, the space between them is immense, making close encounters with other stellar systems an impossibility exceptionally rare occurrence, happening only over millions of years. On the grander scale of our journey, the solar system is currently headed toward a massive cosmic structure known as the Hercules Corona Borealis Great Wall. This is merely one component of an even larger set of cosmic movements, which includes our entire galaxy's trajectory toward the Virgo supercluster. The idea of a galactic year provides a valuable framework for comprehending our planet's immense geological and evolutionary timelines, as major events like continental drift, species extinctions, and the rise of mountain ranges have all taken place at different stages of this cosmic orbit. While you are completely unaware of it in your daily life, our planetary system is in constant, high-speed motion through space. Our galactic address is always changing, and across millions of years this journey profoundly shapes the cosmic environment that surrounds us. Within the asteroid belt resides Ceres, its largest inhabitant, and the only dwarf planet in that region, which harbors some fascinating mysteries. With a diameter of roughly 950 kilometers, Ceres is made up of rock and water ice, and its dark surface is marked by startlingly bright white spots. These brilliant features are heavily concentrated within a large impact basin named a crater, with a most luminous area, known as Cerealia Facula, resides at its center. Scientists have concluded that these dazzling patches are composed of salts, primarily sodium carbonate. Their origin is tied to processes occurring beneath the surface, where salty water from Ceres' interior migrated upwards through fissures. Upon reaching the surface and evaporating into the vacuum of space, this brine left behind the bright mineral deposits. The Dawn mission, which observed Ceres closely between 2015 and 2018, verified that this material was indeed salt, produced by recent cryovolcanic activity, overturning earlier theories that it might be exposed water ice. This finding implies that Ceres might be able to retain heat within its core. It's possible that briny water reached the dwarf planet's surface within the last few million years, which is a remarkably short span of time geologically for an object in the asteroid belt. The discovery of similar salt deposits across other areas of Ceres suggests the existence of deep underground reservoirs of liquid brine. From a distance, Ceres might look geologically dormant, but it actually displays evidence of continuous internal processes. Contemporary models point to a complex inner structure featuring a slushy ice mantle beneath a crust of hydrated minerals. These subsurface reservoirs periodically send brine to the surface through fissures caused by impacts or tectonic strain, and it's thought that the decay of radioactive elements in its interior generates sufficient heat to keep these brines in a liquid state. Ceres stands alone as the only body in the asteroid belt with verified water and associated geological activity. The presence of liquid water is an extraordinary phenomenon given the dwarf planet's weak gravity and frigid temperatures. However, the high salt content dramatically lowers water's freezing point, which allows it to stay liquid for much longer periods. Furthermore, these salt deposits could point to chemical reactions that might lay the groundwork for prebiotic chemistry. While you wouldn't consider Ceres a prime candidate for hosting life, it does share some key traits with the icy moons orbiting the gas giants. Investigating this dwarf planet gives scientists a deeper understanding of how ocean worlds evolve, particularly those located a great distance from the Sun. Its low density, which sets it apart from its rocky neighbors, indicates that a large fraction of its mass is composed of water ice. Although its surface is covered in craters, the luminous salt patches emerge as fascinating anomalies. Unlike other dwarf planets like Pluto or Eris, Ceres is situated in the inner solar system, placing it within easier reach for future exploratory missions. Its distinct surface features, chemical makeup, and geological dynamism have made it a top priority for upcoming sample return or lander-based expeditions. Across our solar system, there are over 290 confirmed moons, a number that greatly exceeds the number of planets. Gas giants, such as Jupiter and Saturn, each possess more than 90 of these natural satellites. They present an incredible variety in size and form, ranging from small, irregularly shaped bodies to colossal worlds larger than the planet Mercury. While the majority of moons are geologically inert, a select few exhibit a level of activity so astonishing it can even surpass that of planets. Jupiter's moon Io holds the title for the most volcanically active object in the entire solar system. Its surface is dotted with hundreds of volcanoes, with some in a state of near-constant eruption. This intense activity is fueled by tidal heating, a result of gravitational forces from Jupiter and nearby moons, which causes continuous lava flows that perpetually reshape Io's landscape. Europa, Another of Jupiter's moons conceals an ocean of liquid water beneath its smooth, icy shell, which may be only a few kilometers thick. The presence of numerous cracks on its surface points to active processes below, and the detection of water vapor geysers near its south pole hints at internal heat. Similarly, Enceladus, a small moon of Saturn, expels plumes of water from fissures in its frozen crust. The Cassini probe actually flew through these geysers and found organic molecules, marking Enceladus as a leading candidate in the search for extraterrestrial life. Triton, Saturn's largest moon, features a landscape with rivers, lakes, and seas composed of liquid methane, all under a dense atmosphere that drives weather patterns and seasons. Although its surface is far too cold for liquid water, a subterranean ocean of water and ammonia might exist far below. Meanwhile, Neptune's largest moon, Triton, displays geological activity despite its vast distance from the Sun. Its backward orbit indicates it was captured by Neptune's gravity, and the lingering tidal forces from that event may still be generating internal warmth. Many of the smaller moons are believed to be captured asteroids, characterized by their irregular forms and distant orbits. Though they are usually geologically inactive, their composition offers crucial clues about the formation of the early solar system. As our telescopic technology advances, the tally of known moons keeps rising. In just the last few years, dozens of new, tiny moons have been found orbiting Jupiter and Saturn, most of which are incredibly difficult to spot. Looking to the future, some of these moons may hold resources that could prove invaluable for space exploration. Water ice, for instance, could be processed into drinking water, breathable oxygen, or even rocket fuel. This potential makes these celestial bodies significant not just from a scientific perspective, but from a practical one as well. Earth is accompanied in its orbit by Trojan asteroids, which are small celestial objects that travel along with our planet, largely undetected. These bodies are held within stable gravitational zones known as the L4 and L5 Lagrange Points, situated 60 degrees ahead of and behind Earth on its orbital path. The very first Earth-Trojan asteroid, named 2010 TK7, was not identified until the year 2010. This object, measuring roughly 300 meters in diameter, traces a complex, tadpole-shaped path around the L4 point, without ever drifting far away. Finding these asteroids is a significant technical feat, because, from our viewpoint on Earth, they are always positioned near the blinding glare of the Sun, which explains why their discovery came so late, and suggests many more may remain hidden. Trojan asteroids have been located near other planets as well, including Jupiter, Neptune, and Mars. Jupiter is home to the largest population of these objects, with more than 10,000 documented Trojans. They can maintain these stable positions for millions of years, thanks to the balanced gravitational pull between the Sun and their host planet. You can rest assured that Earth's Trojans present no threat to us, as they are locked into stable orbits that will never intersect with our own. Because of their distinct orbits and significant distance, there is no chance of a close encounter with Trojan asteroids. Examining these bodies provides a priceless window into the formation of our solar system, as they are believed to harbor pristine materials from the primordial solar nebula. Their stable trajectories have preserved the original conditions of their creation, making them genuine time capsules from a bygone era. You might find it fascinating that some of the most stunning comets we witness originate in the solar system's most remote regions, undertaking a journey toward the Sun that lasts for millennia. These long-period comets are born in the Oort cloud, a mysterious spherical shell that envelops our entire planetary system at distances up to 1/100,000 astronomical units from the Sun. Comets from this area have orbital periods that can be measured in thousands or even millions of years. The trajectories of these comets are often so extraordinarily elongated that many will pass near the Sun just once in all of recorded human history before they are ejected into interstellar space forever. It's important to understand that the Oort cloud has never been directly witnessed. We infer its existence by analyzing the orbits of these very comets. They frequently appear without warning, lacking any discernible source in the inner solar system, and their angles of approach strongly suggest a vast, spherical reservoir of icy objects far beyond Pluto. A slight gravitational push from a passing star, the tidal forces of the Milky Way, or other disturbances can initiate a comet's long fall from the Oort cloud toward our Sun. As it nears our star, the intense heat vaporizes its frozen gases, which produces the signature glowing coma and a spectacular tail. It is these long-period visitors, such as the well-known comets Hale-Bopp and Ison, that often become the brightest and most observable objects in the night sky, usually making only a single pass before they vanish forever. Comets are composed of a mix of water ice, frozen gases, dust, and rocky material, and are considered ancient artifacts from the solar system's formation. It is theorized that objects in the Oort cloud initially formed near the gas giants and were subsequently flung to the system's outer edges by gravitational interactions. When these long-period comets venture into the inner solar system, they offer unique scientific insights, as their composition has remained largely unchanged for 4.6 billion years, giving you a direct glimpse into the past of our cosmic home. The solar wind is a continuous stream of charged particles, mainly electrons and protons, that our star constantly releases into space, traveling at speeds up to 800 kilometers per second. When this stream reaches the vicinity of Earth, it engages in a dramatic interaction with our magnetosphere, the planet's protective magnetic field. This encounter drastically reshapes the magnetosphere, compressing it on the sunlit side and stretching it into a long tail on the night side that extends for millions of kilometers, with the severity of these changes depending on the solar wind's intensity. The strength of the solar wind is highly variable. It can grow much more powerful during solar storms or events known as coronal mass ejections. These occurrences are immense outpourings of solar energy and plasma that, upon colliding with Earth's magnetic field, trigger geomagnetic storms. Such powerful space weather events can significantly disrupt satellite systems, communications, and terrestrial power grids. The breathtaking auroras are a direct result of solar wind particles channeling along magnetic field lines and penetrating the upper layers of Earth's atmosphere. Although our magnetic field is a formidable shield, it cannot deflect all incoming particles. Some become trapped in the Van Allen radiation belts, which are regions of charged particles that pose a considerable risk to satellites and astronauts. This entire interaction also generates complex electric currents in our planet's ionosphere, which can, in turn, induce damaging currents in long metal structures like pipelines and power lines on the ground. Beyond these effects, the magnetosphere fulfills a critical function in safeguarding Earth's atmosphere from being stripped away. Planets like Mars, which lack a significant magnetic field, have lost the majority of their atmospheres over time due to erosion by the solar wind. Our planet's magnetic shield prevents this from happening, which is a fundamental reason why Earth remains habitable. The heliosphere is a vast protective bubble created by the outward pressure of the solar wind and the sun's magnetic field. This immense region extends far beyond the orbits of every planet, marking the boundary between our solar system and the challenging interstellar medium. Inside this bubble, particles from the sun dominate, whereas outside lies a domain filled with galactic cosmic rays and material from other stars. The heliosphere functions as a natural shield, deflecting much of this harmful high-energy radiation and thereby protecting life on Earth. The very edge of this bubble is called the heliopause. It is the point where the solar wind's force finally yields to the pressure of the interstellar medium. Before reaching this final boundary, the solar wind slows down abruptly, at a frontier known as the termination shock. It is beyond the heliopause that you find true interstellar space, a region that the Voyager 1 and Voyager 2 spacecraft have famously crossed, providing humanity with its first-ever direct data from beyond our solar system. The zone, situated between the termination shock and the heliopause, is known as the heliosheath, a turbulent area comprising a mix of solar and interstellar particles. The heliospheric bubble that envelops our solar system is by no means a geometrically perfect sphere. Its form is perpetually warped by the journey of our entire star system through the vastness of the galaxy. You can visualize this cosmic protective shell as having the asymmetrical shape of a comet, with its leading edge remaining somewhat rounded as it encounters galactic matter, while a long, distorted tail trails behind us. The sun's immense magnetic field provides the unseen scaffolding that holds this magnificent structure together. Interestingly, this entire structure rhythmically expands and contracts in tune with the sun's 11-year cycle of activity. During phases of maximum activity, our star ejects more powerful streams of charged particles, which effectively inflate the heliosphere. Conversely, when the sun enters a quieter period, this protective cocoon shrinks slightly, much like a slowly breathing organism. Such pulsations have a direct impact on the amount of galactic radiation that penetrates our star system. Throughout periods of solar minimum, astronauts aboard orbital stations and the electronics within satellites face a heightened risk from cosmic radiation. This reality compels engineers to design supplementary shielding and to meticulously schedule space operations. It is crucial for you to grasp that the heliosphere is not an impenetrable fortress against cosmic rays, as the most energetic particles still manage to breach our defenses and reach the inner solar system. Nevertheless, this natural shield significantly diminishes the total influx of hazardous radiation, which is why the heliosphere is recognized as a fundamental protective mechanism for the existence of life on our planet. For those planning long-range space expeditions, a thorough understanding of heliospheric dynamics is of paramount importance. Once you travel beyond this protective bubble, the radiation environment becomes lethal to humans, which is why missions to Mars and even more distant worlds necessitate either robust radiation shielding systems or precise launch timing to coincide with solar maximum, when our natural protection is at its strongest. The heliosphere is brought into being by the ceaseless outflow of the solar wind and magnetic energy, creating a dynamic, ever-changing frontier rather than a fixed structure. Any variation in our star's behavior is immediately mirrored in the size and shape of this cosmic boundary. By studying these fluctuations, astronomers can achieve a more profound comprehension of processes occurring in both the solar and the wider galactic environments. Ultimately, the heliosphere marks the outermost limit of the sun's influence, isolating our cosmic home from the rest of the galaxy's radiation and ensuring that conditions on Earth remain far more stable and hospitable to life. Within our system, The undisputed record for light absorption belongs to the enigmatic planet Uranus. This world reflects a surprisingly small amount of solar radiation, establishing it as the darkest among the major celestial bodies. Despite the distinctive bluish-green color you see in telescopic images, Uranus possesses one of the system's lowest reflectivities. Its albedo, which is the measure of this reflectivity, is approximately 0.3, indicating that it bounces back only 30% of the sunlight it receives, making it the clear champion of light absorption. The underlying reasons for this exceptionally low albedo continue to be a topic of scientific inquiry. Researchers theorize that the primary cause might be a thick layer of haze located in the planet's upper atmosphere. This mysterious haze appears to actively absorb solar rays rather than scattering them back into space. In contrast to its neighbor Neptune, which has a similar composition but a much brighter appearance, Uranus consistently looks muted and dull in every image captured of it. Uranus's atmosphere is composed mainly of hydrogen, helium, and methane. It is the methane molecules that absorb red light while reflecting blue light, which accounts for the planet's signature bluish-green tint. However, the enigmatic haze layer seems to act as a shroud over the methane clouds, drastically cutting down the amount of light that can escape back into space. This phenomenon is a major contributor to the planet's dark and subdued appearance. Observations from telescopes and spacecraft reveal that Uranus is almost completely lacking in visible cloud structures. When compared to the intricate atmospheric patterns of Jupiter and Saturn, it looks astonishingly plain and featureless across most of the electromagnetic spectrum. This absence of contrasting features likely contributes to the planet's reduced overall capacity to reflect incoming light, resulting in extremely low visual activity from an Earth-based perspective. The historic Voyager 2 mission, which performed a flyby of Uranus in 1986, delivered our most detailed images of this world to date. Even in those close-up views, the planet presented a largely featureless and dim facade, confirming suspicions about atmospheric processes that suppress its reflectivity. Modern models now propose that this haze layer is made of complex hydrocarbon compounds, formed when solar radiation breaks down methane molecules. The latest data from the Hubble Space Telescope and the world's largest ground-based observatories affirm that Uranus consistently remains darker than anticipated. Adding to the mystery, Uranus's internal heat emission is unusually low. Unlike Jupiter, Saturn, and Neptune, this ice giant radiates almost no excess heat from its core. This characteristic profoundly influences its atmospheric dynamics, likely contributing to its static and placid appearance. With less internal heat to drive weather systems, there is reduced activity in terms of storms, cloud formation, and internal circulation, which may allow the light-absorbing haze layer to persist for extended periods. The progression of seasons on Uranus is dictated by the planet's exceptionally dramatic axial tilt, which exposes each of its hemispheres to sunlight for decades at a time as it orbits the Sun. Despite these prolonged periods of illumination, there is remarkably little variation in its reflectivity, meaning its dark appearance remains consistent regardless of the season. To better grasp the atmospheric dynamics and associated chemical reactions at play, scientists are continuously refining their computer simulations of Uranus. The planet's low reflectivity is a crucial element in distinguishing it from Neptune, as both worlds share similar dimensions and chemical makeup, but possess starkly different light-reflecting properties. Ultimately, Uranus reflects a minimal amount of light due to layers of haze in its atmosphere and a general reduction in atmospheric activity. This results in a muted appearance that makes it the darkest major planet in our solar system, a fact that contrasts with its vibrant hue in telescopic images and remains an unexplained anomaly among gas giants. Venus showcases a truly peculiar rotational characteristic, as it spins in the opposite direction of most other planets within our system. This planet exhibits what is known as retrograde rotation, turning from east to west in a manner completely contrary to the standard planetary spin. Furthermore, its rotation is exceedingly slow, with a single turn on its axis taking approximately 243 Earth days, which is notably longer than its orbital period of about 225 Earth days. Consequently, a day on Venus lasts longer than its year, a genuinely stunning astronomical fact. This type of backward spin is exceptionally rare in our solar system, with only Venus and Uranus displaying such behavior, though their axial inclinations are vastly different. Venus has an axial tilt of about 177 degrees, which means the planet is essentially oriented upside down. The scientific community has not yet settled on a definitive cause for this reversed rotation. One prominent explanation proposes that a colossal impact with another large celestial object occurred early in the planet's formation, an event that could have drastically altered its spin or shifted its rotational direction over geological time. An alternative theory connects this strange behavior to the sustained gravitational pull of the Sun and adjacent planets. It's possible that tidal forces from our star played a significant role, as Venus possesses an incredibly dense atmosphere with which solar gravity could interact far more powerfully than it does with planets having thinner atmospheric layers. Over billions of years, this influence might have gradually slowed down and eventually reversed the planet's rotation, though such a process would have taken an immense amount of time. Remarkably, the rotation of Venus demonstrates a high degree of stability. Unlike Earth, it doesn't exhibit significant wobbles or precessional movements of its axis, despite its extremely slow and backward spin. This suggests its current rotational state has been maintained for vast geological eras, and the planet displays no indications of any potential changes to its spin in the foreseeable future. The retrograde rotation leads to a curious effect. If you were on Venus, you would see the sun rise in the west and set in the east. However, because of the planet's slow turning speed and the motion of its thick, opaque cloud cover, a complete cycle from sunrise to sunset would extend over many Earth weeks. The dense atmosphere also scatters sunlight extensively, illuminating the surface with diffused light rather than direct rays. This unique rotation has a profound impact on Venusian weather patterns and cloud formations. The planet's atmosphere spins much more rapidly than its surface, a phenomenon referred to as superrotation, with wind currents in the upper layers circling the entire planet in just a handful of Earth days. This results in the swift movement of cloud masses, even as the planet itself turns at a crawl. The reverse spin also influences models of the planet's internal structure and core, which is thought to be structurally similar to Earth's. The planet's unusual rotation may alter convective processes within its core and affect the generation of magnetic fields, which could explain why Venus lacks a global magnetic field. Future missions, such as the Veritas and Da Vinci Plus projects, are expected to help unravel the mechanisms and origins of the planet's distinct rotation by studying both its surface geology and atmospheric dynamics. A clearer understanding of these rotational properties could offer invaluable clues about how planetary systems form and evolve over time. The retrograde rotation of Venus stands as one of the most extreme and enigmatic characteristics in our solar system, setting the planet apart in its daily cycles and geological past. While the reason for this behavior remains a topic of scientific debate, it is undeniably a central factor in how the planet functions today. Mars, much like our own world, goes through 4 distinct seasons, but each one lasts nearly twice as long as it does on Earth. The red planet experiences its own versions of spring, summer, autumn, and winter, which are driven by the tilt of its axis. At approximately 25 degrees, its axial tilt is strikingly close to Earth's 23.5 degrees, causing sunlight to hit different regions at varying angles throughout the year, and thereby creating seasonal shifts in temperature and weather. However, a Martian year is equivalent to 687 Earth days, which means that every season on the red planet lasts about double the length of its terrestrial counterpart. For instance, summer in Mars's northern hemisphere can persist for as long as half an Earth year. This extended duration profoundly influences the planet's atmospheric circulation and surface conditions. Additionally, Mars follows a more elliptical orbit than Earth, which results in seasons of unequal length. The seasons on Mars present a stark contrast between its hemispheres. The northern summers are extended and gentle, whereas the southern summers are brief yet severe. This disparity is a direct result of the planet's elliptical orbit, which brings it nearer to the Sun when the southern hemisphere is tilted towards it, creating dramatic temperature variations between the two regions. As winter takes hold, the sparse Martian atmosphere sees its carbon dioxide freeze and settle onto the surface, creating polar ice caps. Conversely, with the arrival of summer, this frozen carbon dioxide undergoes sublimation, turning directly back into a gas, which elevates the planet's overall atmospheric pressure. This fundamental seasonal process is a key driver of major weather events, including the formation of clouds, shifting wind patterns, and powerful dust storms, causing the entire atmosphere to effectively breathe, expanding and contracting with the changing seasons. The intense solar radiation during the southern hemisphere's summer frequently triggers massive dust storms, which are fueled by the seasonal variations in how the ground is heated. These atmospheric upheavals can grow to an enormous scale, sometimes enveloping the entire planet for weeks at a time. When this happens, the dense dust clouds can obscure the sun, causing surface temperatures to plummet dramatically. A global storm of this magnitude ultimately led to the loss of NASA's Opportunity rover in 2018. The climate on Mars is characterized by extreme temperature swings that are dictated by both season and location. For instance, daytime temperatures in equatorial areas can reach a pleasant 20 degrees Celsius in the summer, yet polar regions in winter can plunge below a frigid -70 degrees Celsius. Because its atmosphere is so thin, the planet struggles to hold on to any thermal energy, allowing for conditions so cold that frost and ice can appear even near the equator during certain times. The planet's seasons also profoundly influence the polar ice caps, which consist of a mixture of both water ice and frozen carbon dioxide, or dry ice. These vast ice formations expand and recede in tune with the seasonal cycle, and in doing so they reveal distinct, layered deposits. These geological strata are crucial for scientists, as they contain a remarkably well-preserved record of Mars's past climate, offering deep insights into its long-term weather patterns. Robotic explorers such as Curiosity and Perseverance are tasked with continuously tracking seasonal shifts at their respective locations. As Mars orbits the Sun, they record fluctuations in key environmental factors like atmospheric pressure, the amount of dust in the air, and the strength of the sunlight. The information they gather is vital for helping scientists comprehend Martian weather and assess how it affects everything from rover operations to the performance of solar panels. A thorough understanding of these seasonal cycles is therefore absolutely essential for planning successful missions to Mars. Factors like the amount of available solar power, the operational temperature range, and the density of atmospheric dust fluctuate dramatically throughout the year. Strategically selecting a landing time to bypass the harshest weather, especially the infamous dust storms, significantly enhances the probability of a mission's success, and also informs the search for water and potential habitats. The prolonged and highly variable Martian seasons highlight both the similarities and the stark differences between Mars and our own world. While Mars experiences recognizable patterns like solstices and equinoxes, they unfold on a much longer and more severe timeline. Gaining insight into these cycles is crucial for planning future long-term exploration and potential human missions, and it underscores the importance of factors that stabilize our own climate, chief among them being the Moon's influence on Earth's axial tilt. The familiar rhythm of our seasons is a direct consequence of Earth's 23.5-degree axial tilt, and the stability of this tilt is maintained almost entirely by the gravitational pull of our Moon. Were it not for our large satellite, Earth's rotational axis would experience far more dramatic shifts over geological time. In fact, computer simulations suggest that without the Moon, this tilt could oscillate by as much as 60 degrees, which would trigger devastating and chaotic climate change across the globe. This stabilizing phenomenon is a result of tidal forces, where the Moon's gravity exerts a consistent pull on Earth's equatorial bulge as our planet spins, generating a corrective torque. This force effectively counters the destabilizing gravitational influences from the Sun and the other planets in our solar system. Consequently, the Moon keeps our planet's axial tilt confined to a very narrow and predictable range, a condition that has persisted for the millions of years required for life to evolve. The angle of our planet's axis is the primary factor that dictates how much solar energy different regions receive over the course of a year. If this tilt were to alter erratically, the poles could become as warm as the tropics, while equatorial regions might find themselves locked under sheets of ice. Such instability would render long-term climate predictions impossible and would cause complete chaos for global ecosystems and the cycles of agriculture, demonstrating how crucial a stable axis is for sustaining life. Sophisticated simulations confirm that without the Moon, Earth's axis would wobble unpredictably over vast spans of time, much like what we observe with Mars. Lacking any large natural satellites, Mars undergoes massive variations in its axial tilt, shifting by tens of degrees over geological epochs. Our Moon serves as a vital gravitational anchor, preventing our own planet from succumbing to this kind of climatic chaos. While the Moon is famous for creating ocean tides, its stabilizing function is a separate effect that relies on its sheer mass and its proximity to Earth, not the tides themselves. A satellite that was smaller or orbited farther away would be incapable of providing the same degree of axial stability, highlighting the unique properties of our lunar companion. The Moon is unusually massive in relation to Earth when compared to other moons and planets in the solar system, a feature that likely resulted from a colossal impact in our planet's distant past. The leading theory suggests that a Mars-sized body struck the early Earth, and the debris from this collision eventually coalesced to form our satellite, creating the very system that ensures our long-term stability. Earth's tilt isn't perfectly static. It oscillates gently between 22.1 and 24.5 degrees over a 41,000-year period as part of the Milankovitch cycles, which are known to affect ice ages. However, these predictable shifts are minor compared to the wild fluctuations the Moon's presence prevents. Finally, Jupiter serves as a kind of cosmic guardian for the inner solar system, including Earth. As the most massive planet, its immense gravitational field acts as a shield, deflecting the trajectories of comets and asteroids that could otherwise pose a significant threat to our world. Jupiter functions as a gravitational guardian for Earth and the other inner planets, capable of capturing, deflecting, or even flinging away inbound comets and asteroids. This protective role is a direct result of its enormous mass and strategic location in the solar system. The planet's immense gravitational pull is strong enough to fundamentally change the path of celestial bodies that venture too close. Many of these objects are either expelled from our solar system entirely or drawn directly into Jupiter's atmosphere. We have witnessed several major impacts on the gas giant, most notably the collision with comet Shoemaker-Levy 9 back in 1994. After breaking apart, the comet's fragments slammed into Jupiter, creating enormous, dark impact sites that vividly illustrated how the planet absorbs threats that could otherwise be on a trajectory for Earth. Because of Jupiter's presence, the quantity of potentially dangerous impacts reaching the inner planets is substantially lowered. While this doesn't eliminate every single threat, it drastically lessens how often they occur. This function as a celestial guardian is a cornerstone concept in the fields of planetology and the search for life beyond Earth. Jupiter's influence extends to the asteroid belt situated between its orbit and that of Mars, where its gravity establishes orbital resonances that organize the asteroid's distribution. Although these same forces can sometimes destabilize asteroid orbits and send debris careening toward the inner solar system, the planet's overall effect is one of control, preventing the belt from coalescing into a new planet. While it's true that Jupiter's gravity can occasionally nudge comets onto paths toward the inner solar system, statistical analyses confirm that it averts far more collisions than it initiates. The planet's gravitational interactions are intricate, yet its net influence is undeniably protective over vast timescales. It is almost certain that without Jupiter, Earth would face a much higher rate of devastating impact events. The gas giant is accompanied by a large family of moons, and some, like Ganymede and Callisto, may play a secondary role in this shielding process by capturing or deflecting smaller objects. Nevertheless, Jupiter itself is the principal defender, its dominance cemented by its sheer mass and pivotal position as the primary gravitational power in the outer solar system. Computer models simulating the development of planetary systems frequently incorporate the effects of planets similar to Jupiter. These simulations suggest that systems lacking a gas giant in a comparable orbit are far more susceptible to impacts from cosmic debris. Consequently, the lack of such a guardian planet in other star systems might significantly reduce the chances of life developing on their terrestrial worlds. Jupiter's orbit has a mild eccentricity and has been remarkably stable for billions of years, enabling it to consistently perform its protective duties across geological time. Had the planet settled into a different orbital pattern, its effect on the paths of asteroids and comets would be far more chaotic. Its present location appears to be perfectly suited for its role as a planetary shield. Turning our attention to the outer solar system, Uranus and Neptune stand out as the two major planets we know the least about in contemporary astronomy. Often called the ice giants, they are fundamentally different from Jupiter and Saturn. whereas the gas giants consist mainly of hydrogen and helium. These distant worlds have interiors rich with water, methane, and ammonia ices. Despite their substantial size and scientific significance, these planets are remarkably unexplored, with only the Voyager 2 spacecraft having ever performed flybys. It provided our only close-up views, reaching Uranus in 1986, and then Neptune in 1989. Ever since that brief encounter, our knowledge has been gathered solely through telescopes, leaving our comprehension of their atmospheric dynamics, magnetic fields, and deep interiors severely restricted. Numerous mysteries still surround the composition and dynamics of these two worlds. Uranus, for instance, has a peculiar rotation, tilted on its side at an angle of roughly 98 degrees, which may be the consequence of a massive impact deep in its history. Furthermore, its magnetic field is dramatically skewed and displaced from the planet's core. Neptune, by contrast, possesses a more conventional axial tilt, but showcases an incredibly active atmosphere. It features massive storm systems and sustains wind speeds reaching up to 2,000 kilometers per hour, which are the highest recorded anywhere in our solar system. Both planets are adorned with faint ring systems and a multitude of moons, and both experience complex weather, yet their deep interiors are still a complete enigma. Current theories propose that beneath their clouds lies a hot, slushy mantle made of water, ammonia, and methane. But no spacecraft has ever been able to directly verify this. The magnetic fields of both Uranus and Neptune are erratic and misaligned with their axes of rotation, hinting at strange processes occurring within them. Unlike on Earth or Jupiter, where magnetic fields are produced by rotating metallic cores, the mechanism on the ice giants might originate from electrically conductive oceans or peculiar phases of ice. Advanced observatories, particularly the James Webb Space Telescope, are starting to deliver superior data on these distant worlds, allowing us to analyze their atmospheric makeup, temperature gradients, and cloud formations. However, even with these powerful new instruments, a true understanding of these planets will only come from dedicated space missions. As of now, there are no spacecraft en route to either of these planets, though space agencies are evaluating potential future projects like orbital missions to Neptune or atmospheric probes for Uranus. Such expeditions would investigate not only the planet's compositions and rings, but also their moon systems, which are a significant focus of scientific interest. These missions, however, present enormous technical hurdles due to the immense distances and lengthy travel durations, with journeys taking over a decade using our current capabilities. Neptune's largest moon, Triton, is thought to be a captured object from the Kuiper Belt and might still be geologically active. Similarly, the moons of Uranus exhibit evidence of historical tectonic activity and could harbor oceans beneath their surfaces. These compelling ideas, however, will stay as unconfirmed hypotheses without direct, in-depth investigation. Gaining a deeper knowledge of our ice giants is essential for the field of comparative planetology, especially since a large number of discovered exoplanets share a similar size and mass with them. Analyzing Uranus and Neptune would provide scientists with the necessary context to more accurately decipher data from remote planetary systems. As it stands, these two worlds represent a vast, mostly unknown frontier in our own cosmic neighborhood. They are unique in being the only major planets that have never been studied by a dedicated orbital mission. Consequently, dispatching research probes to these distant giants is regarded as one of the foremost priorities for planetary science in the upcoming decades. Mercury is subject to some of the most severe temperature variations found anywhere in our solar system, with its climate swinging from a frigid -170 degrees Celsius at night to a blistering +430 degrees Celsius in the daytime. As the planet closest to the Sun, Mercury is missing a substantial atmosphere that could trap and redistribute thermal energy. This absence is the direct cause of the dramatic temperature shifts its surface endures. By day, the surface can get as hot as +430 degrees Celsius, a temperature sufficient to liquefy certain metal alloys, while at night, it plunges to around -170 degrees Celsius, far colder than any naturally occurring temperature on our planet. This constitutes one of the most extensive temperature ranges observed on any planetary body. The core reason for this volatility is the lack of a significant atmospheric blanket. Mercury only possesses a very thin exosphere, made of atoms blasted from its surface by the solar wind and micrometeorite strikes, which is incapable of retaining heat like the atmospheres of Earth or Venus. This extreme temperature effect is further intensified by the planet's exceptionally slow rotation. A single solar day on Mercury, measured from one sunrise to the next, is equivalent to about 176 Earth days. This results in each hemisphere of the planet experiencing very long stretches of either relentless solar heating or deep radiative cooling into space. These prolonged periods of day and night are a major factor in the massive temperature changes, as there is no substantial buffering system to stabilize the surface conditions. In the daytime, Mercury is bombarded with solar radiation approximately 7 times more powerful than what reaches Earth, and its rocky surface absorbs this energy directly, without the benefit of atmospheric scattering or cloud cover. At night, the absence of atmospheric insulation leads to a precipitous drop in temperature, as the rocks and regolith radiate their stored heat away at a remarkable speed. The coldest locations are found in the permanently shadowed polar craters, some of which are cold enough to maintain deposits of water ice, a remarkable feature for a planet so close to the Sun.